Welcome to the Explainer. Today, we're going to tackle one of the most powerful and, honestly, one of the most beautiful tools in all of mathematics, the Taylor series. It's this incredible idea that lets us understand and work with even the most complicated functions by using the simple building blocks of polynomials.
Okay, let's just dive right in. Just watch what happens on the screen here. We start with a plain old straight line, right? Then a bit of a curve. And then, with each new piece we add, our simple polynomial starts to wrap itself tighter and tighter around that wavy sine function. It's kind of like we're watching it learn how to perfectly impersonate a much more complex shape.
And this just makes you wonder, right? How is that even possible? How can we use something as basic as a polynomial? I mean, it's just adding and multiplying stuff to describe the kinds of complex curves that show up everywhere, from planetary orbits to electrical signals. And more importantly, why is this trick so unbelievably useful?
Well, the big idea at the heart of it all is brilliantly simple. A lot of the functions you run into in science and engineering, they're really hard to work with. The Taylor series gives us this amazing way to trade in a hard function for an easy one, a polynomial, that acts almost exactly the same, at least around the specific spot we care about.
So let's get into the nitty-gritty of how we actually build this perfect mathematical impersonator for basically any function we come across. Now, the official term for this whole process is polynomial approximation. And this is the key that really unlocks the power of the Taylor series. It lets us simplify these gnarly calculations and analyze things that would otherwise just be way too complicated to handle.
All right, let's see how this thing gets built. We're going to put our approximation together piece by piece, and you'll see it's actually a really intuitive idea. You know, even if calculus gives you a headache.
You know, what's really cool about this is how logical it is. Think about it like this. Step 1, you pin the two functions together at one point. That's like matching their position. Step 2, you match their slopes, so now they're moving in the same direction. That's like matching their velocity. Step 3, you match their curvature. That's like matching their acceleration. And if you just keep going, your polynomial becomes a better and better mimic.
So what happens if we take that process and we just don't stop? What if we continue it not just 3 or 4 times, but forever? Well, then we get the complete recipe for our perfect impersonator. We get the Taylor series.
And here it is. This is the formal definition, figured out by Brooke Taylor way back in 1715. This formula, it's the whole instruction manual. It tells you exactly which numbers to plug in, all based on the function's behavior at just one single point, a, to build this infinitely long polynomial.
Now, you're probably going to hear about something called the Maclaurin series. It was named after Colin Maclaurin. But don't let the new name throw you. It's just a Taylor series that's centered on the most convenient point you could possibly pick, 0. Honestly, it's the version you'll see most of the time. And this is where the magic really happens. Just look at this table. Some of the most fundamental, most important functions in all of science, e to the x, sine, cosine, can all be perfectly rewritten as these simple, infinite polynomials. It's like having the source code for the universe.
But, you know, with any tool this powerful, there's always a little bit of fine print, isn't there? There's a really important catch we have to talk about. Does this approximation always work, no matter what number we plug in for x?
So here's the deal. For some functions, like e to the x or sine, our impersonation is perfect. It works everywhere, all the way across the number line. But for others, like the natural log here, the impersonation is only convincing in a certain neighborhood. If you go too far away from where you started, the approximation completely falls apart and becomes useless.
What's amazing, though, is that we can be incredibly precise about how good our approximation is. There's something called the remainder estimation theorem that lets us calculate the exact error. So, for example, if you're an engineer and you need your approximation of sine to be accurate within this tiny number, the theorem will tell you exactly how many terms of the series you need to add to guarantee you're that close.
Okay, so this might all seem a little bit abstract and theoretical. But in the real world, this thing is a scientific superpower. Let's see how it's actually used to solve real problems. Let's take a classic problem, something you'd see in a first-year physics class, calculating the electric potential at some point far away from an electric dipole. And a dipole is really just a positive and a negative charge that are stuck close together.
Now, if you try to solve this using the exact formula from the textbook, you end up with this algebraic nightmare. It's got square roots and fractions inside of fractions. It's really hard to work with, and it's almost impossible to look at it and get any simple, intuitive feeling for what the answer means.
But
we have a secret weapon. Remember that table? There's a Taylor series called the binomial series, and it tells us that for a really small x, we can use this super simple approximation. This is literally just the first two terms of the full Taylor expansion.
And by applying just that one simple approximation, the whole messy physics problem just transforms. The complicated algebra collapses, and suddenly we're left with a clean, simple, and really meaningful result for the electric potential. And I'm not kidding, this is the kind of thing physicists and engineers do every single day.
And this technique is absolutely everywhere. It's used to model the swing of a pendulum, to process signals and control systems. It's literally how your calculator figures out the sign of a number, or e to the x. It's even used to show how Einstein's theory of relativity simplifies down to regular old classical physics when you're not moving too fast.
So that kind of leaves us with a final thought. The Taylor series is way more than just a math trick. It teaches us a really powerful way of thinking. To understand a massively complex system, sometimes the best way is to just find a simple local model that's good enough. And it really makes you wonder, right? From the economic models we rely on to the mental shortcuts we all use every day. Where else are we using a good enough approximation to make sense of a really complex world?